Okay, so in this example, we're going to find the vertical and horizontal asymptotes for the function f of x equals 3x minus 2 over the expression x squared plus 7x plus 12. Now I've already graphed in here in Desmos, so you can kind of see that at the bottom, I lost my little, there it is. So you can see in the bottom that we have this little almost asymptote looking thing. A lot of calculators, though, it gets a little funky around asymptotes. You can see stuff flickering right there. It doesn't actually exist there, but you can see it flickering. The rest of the graph is actually up there. A lot of times graphing utilities have a lot of trouble with those vertical asymptotes. And some calculators will even stop graphing the vertical asymptotes as they go. So you can kind of see it flickering as I move. But to find vertical asymptotes, to start with, vertical asymptotes come from where the bottom of the fraction is equal to 0, but not the top. So we're not going to really focus on what happens when the top's also equal to 0, at least during this particular example. But it is important to check the top as well. So for the vertical asymptotes, what I'll have to do is I'll have to factor the bottom here. My top's already factored. You can't factor that top, but the bottom we will need to factor. So we'll go ahead and multiply our first and last. I'll just kind of do it up here. Give us 12x squared. And I'm going to jump straight to the combination. Normally I take a little bit longer to go through it. The combination that adds up to the middle term is 3 and 4. And since there is no leading coefficient, we can jump straight to the actual factors of x plus 3 and x plus 4 for the factors. You'll notice that the factors on the bottom do not match the factors on the top. So every factor in the bottom will create an asymptote. So what we'll do is we'll apply zero product property, setting the bottom of our fraction equal to 0. So x plus 3 times x plus 4 equals 0. Because again, vertical asymptotes come from where the bottom of the fraction is equal to 0, but not the top. Since the factors are not the same on the top and bottom, they won't have any overlapping places. So we just have to focus on the bottom here for this example. We'll use zero product property to set each factor equal to 0 and solve. So we'll have one vertical asymptote taking place at x equals -3, and the other one taking place at x equals -4. So those are the vertical asymptotes. I'm going to pull up Desmos here and just actually type those in. So x equals -3, and then x equals -4. I'm going to go ahead and actually change the type to dash line because that's how asymptotes are typically portrayed. And here I'll expand it and just take a closer look at this graph. So that's how we find vertical asymptotes. Those are my vertical ones. For horizontal asymptotes, at the very least in Algebra 2 here, we're going to use a property. This property, you explore where it comes from in calculus and talking about limits. But we're going to be looking at these three cases to determine the end behavior. You examine it more in calculus and anything to do with limits. But the first case is where the degree of the denominator, or the bottom, if you have trouble remembering which one is which, is greater. So if the higher exponent's on the bottom, then the horizontal asymptote will be y equals 0. If the degree of the numerator, which is the top of the fraction, if you have trouble remembering, if it's greater, then there is no horizontal asymptote. And then lastly, if the degree of the numerator and denominator is equal, then this is kind of the weird one. The horizontal asymptote will be the ratio of leading coefficients. So in the case of this example here in the property, we have the degree the same on top and bottom. So it's a ratio of the leading coefficients, which deals with the 2 and 3. So the equation for the horizontal asymptote is y equals 2 over 3. So let's go back up to our equation here. So if we look right now, the higher degree is on the bottom. The top just has an exponent 1, so our higher exponent is on the bottom. So for the horizontal asymptotes, it's going to follow case 1, which means our horizontal asymptote will be y equals 0. And that's actually it for the horizontal asymptotes, just applying that property. But I do want to take one more look at the graph. So y equals 0. We'll go ahead and change that to be a dotted line, just like I did with the others. Then I'll make my graph nice and big. So you can kind of see what's going on here. You can see the asymptotes. They hug it very nicely in between the two things. Those asymptotes were just found by saying the bottom factors equal to 0. We also have a horizontal asymptote as well. And there we have it. So in this next example, we are going to be graphing a rational function. We're going to use some basic techniques here to do it. So as far as doing stuff by hand, we're not going to always have a 100% accurate graph because some of it might require some sort of calculus thing to do it without using a graphic calculator. But we're going to kind of go through these 3 basic steps using these properties, and then we're also going to be comparing it to the graph that a graphing calculator would also give us. So the 3 steps we're going to do is find and graph the vertical asymptotes. We're going to then find and graph the horizontal asymptotes, and then we're going to choose x values on each side of asymptotes. Specifically, because we're choosing x values on each side of asymptotes, that's going to be oh yeah, that describes it. But it's going to be the vertical asymptotes. Yes, that's why I wanted to add vertical asymptotes. And then we're going to evaluate it to finish the graph. So let's get started. So first of all, let's find the vertical asymptotes. Vertical asymptotes comes from the factors on the bottom where the bottom of the fraction equals 0, but not the top. So if we look at the factors, we can tell that. So I'm going to have to factor. The top is actually a pattern. Both terms are perfect squares. The first one there is 2 squared. And the second one is 3 squared. So it's the a squared minus b squared pattern, which factors are a plus b and a minus b. So the factors of the top would be 2x plus 3 and 2x minus 3. In the bottom here, factors for this, there's no common monomial. It's not a pattern, so we'll multiply first and last, which gives us negative 15x squared. The combination of factors that will add up to be our middle term is positive 5 and negative 3. And since there's no leading coefficient, we can jump straight to the factors. So x plus 5 and x minus 3. Okay. Notice there are no shared factors that are on the top that are also on the bottom. So the entire bottom will create our vertical asymptotes. We're not really focusing on when it's the same during this lesson, but we will in the future. But since there's no common factors on top and bottom, we're going to go ahead and set the bottom of the fraction equal to 0 to find our vertical asymptotes. Using zero product property, we'll set each factor equal to 0. So x plus 5 equals 0, and x minus 3 equals 0. Subtract 5. So x equals negative 5 is one of our vertical asymptotes. and add 3. X equals 3 is our other vertical asymptote. So we're going to go ahead and plot those. At -5, we'll have a vertical asymptote. It looks like my graph is counting by 4s. So that would be about right here. Maybe not 100% accurate, but that's fine. And we also have x equals 3, which would be about right here. There we go. So that's my vertical asymptotes. Let's go ahead and find my horizontal asymptotes. So let's see, horizontal asymptotes. Horizontal asymptotes, we're going to look at the original equation since this is the distributed out one and compare the degree of the top and bottom. Here, you can see that the degree is the same for the top and bottom. Therefore, the horizontal asymptote will be a ratio of the leading coefficients, which in this case is 4 for the top leading coefficient and 1 from the bottom leading coefficient. In other words, the horizontal asymptote is y equals 4. So horizontal asymptote at the y value of 4. There we go. Now we have all those. Now we just need to get some y values to help us finish this graph. And again, this is not going to be 100% accurate because our base knowledge of what we're using is not enough to get super good on the details. But we're going to pick x values in each of these regions to allow us to figure out which section, whether it's this section or this section, or this section and this section, or this section and this section, our function is going to be in. And it may actually cause some issues, but that will be okay. Like I said, we're just exploring here and just learning to graph it a little bit by hand. So I'm going to go ahead for the first one and just pick, let's go with -8. So let's go with the x value of -8. So we're going to do f of -8. We'll do, 0 is the greatest, so in the middle we'll choose f of 0. And then for the last one, let's go with +8 since we chose -8 earlier. Okay, so those are the 3 values that we're going to use here. And we'll just plug them into my equation. Okay, so I've scrolled down a little bit and wrote my equation out so I can see it again. But I'm just going to go ahead and plug x into each of the equations. So we're going to do 4 times -8 squared minus 9. And then we'll divide it by -8 squared plus 2 times -8 minus 15. Going through, we'll do each of those operations. I have no clue what those are. Okay, so going through, just kind of using a calculator to help with some of the operations here to make it go smoother. On the top, if I type that in, we got 247. On the bottom, going through, typing that in, we got 33. Then if we divide it through, and normally I avoid decimals, but for the graph, decimals might be a little bit easier to use. We have 7.484. Just cutting off at 3, I didn't actually round. Plugging 0 in, we're going to have 4 times 0 squared minus 9 over 0 squared plus 2 times 0 minus 15, simplifying to be -9 over -15, which would be, as a decimal is what I wanted, 0.6 as a decimal. And then the last one is a +8, so going through and do the same thing. 4 times 8 squared minus 9 over 8 squared minus, or plus 2 times 8 minus 15, which is going to give me another 247, but this time over 65, which is approximately 3.8. Okay, with that, we're ready to go ahead and plot some points. So my first point is at negative 8, comma 7.4. So negative 8, comma 7.4 would be about here, which means in that first section, my graph is probably going to go something like this, hugging the asymptote, curving through the point, and hugging the asymptote. The second point is at 0.6. So 0.6 is about, remember that this blue horizontal asymptote is at 4, so 0.6 would be probably about right there. So based on what I do have, I'm probably going to guess that it's going to hug the asymptote, curve in through this point, and then hug the asymptote on the other side. That may not be 100% accurate, but we'll check it in a minute and see. Make any adjustments that we have to. And the last one is 8, 3.8. So 8, 3.8 would put it just below that horizontal asymptote, which based on what we have, it would be something like this. Now, many times, not always, but many times, these end spots are in the same direction. So there might be something funny going on, because I would expect that that last one would be up here. It's not always the case, but many times it is. So let's go ahead and take a look at Desmos here and see what we got. So pop over to Desmos. So here is the actual graph. So I would probably say that our middle one is pretty good and our left one is pretty good as well. But you can see that this one is off. And the reason for it is it dips down. It actually crosses the asymptote there. Now, that's not actually a problem. I know the definition I usually use is that it never actually reaches. But what's actually happening is it does dip down. And then as I go, instead of hugging it from above, it actually hugs it from below, hugs that asymptote from below. So at the very end, it never actually reaches that spot. It does get close because the asymptote is more about what's happening as we approach infinity instead of what's happening in the middle of the graph. So it looks like this right side is what we have to fix on our graph. So we're going to hop back there and fix that up. And that's just because with our techniques right now, it'd be hard to tell because we don't have a way of doing increasing, decreasing algebraically. So we're going to draw it down like this, hugging that asymptote, curving through this, but then hugging the blue one from below. So like that. And that's about as good as we can probably draw it hand-drawn. And that's everything. Okay, so while this isn't the focus of this particular lesson, I did want to actually explore it here in the video. And I talked about whenever, I forgot what equation that I'm using, whenever you have a factor that's also on the top as well as the bottom, it doesn't actually create an asymptote. What happens is it creates a hole, as you can see by the lovely little slide here. So just to explore that real quick. So if we were to try to find the vertical asymptotes, we would factor the top and bottom. The top of this particular equation is array factored. The bottom is a pattern, and we'll factor into x plus 3 and x minus 3. You'll notice this time, though, that x minus 3 is in the top and the bottom, and instead the x minus 3 creates a hole. If we don't check to see if there's any overlapping factors, we would just go on and set each factor in the bottom equal to 0 and solve, giving us x equals -3 and x equals +3, thinking none the wiser, and then going to graph it, thinking that there would be an asymptote in both. If I pull up Desmos, however, so I already have it graphed, here's the expected asymptote, but you can see that there's not actually an asymptote there. It just goes straight through it, and nothing really kind of follows along with the asymptote at one of those values. What's actually happening, if I zoom in here, let's see if it will cooperate with me. If I trace over my graph in red, as I move towards that spot, you'll see just an instant right there, undefined. So what's happening is that instead of it creating an asymptote, it actually creates just an undefined value, just a missing point at whatever this y value actually is. And that is actually coming from this, that was at +3. So it's coming from this factor x minus 3, which is the factor that we see on both top and the bottom of the fraction. So if there is an overlapping factor, it actually creates what's called a hole instead of an asymptote. It's one of the big things with calculus and continuity that you examine. This function is not continuous at that point because of that hole. But most graphing utilities, you wouldn't actually be able to see it. And in fact, if you look at the Desmos graph, you can't even see it there unless you drag your pen or finger across it. So if you're not intentionally looking for it, you won't know it's there at all. But yeah, that's just the exploration and why we check to see if there's any overlapping factors, even though that's not something we had actually focused on for the other examples.